Hello, in this video we're in the multiple linear regression setting and we're going to look at the global f-test in this model. So our model is y is equal to x beta plus some error, and since we're going to do a test we have to assume some distributional properties, and the normal assumptions are that the epsilons are multivariate normal with the mean vector 0 and variance covariance matrix sigma squared I. And the global f-test is this. The null is that beta I is 0 for all I equal 1 to k. So every beta parameter, not counting beta 0, every beta parameter associated with the regressor, a predictor variable, or hey, is one of them not 0. In reality, this is probably the first test to consider. Are any of the predictors useful at predicting y? That's what this test is stating. And if the answer is yes, then you can start doing subset tests and partial F's and t-tests and general linear hypotheses tests. So now let's investigate this model under the null hypothesis. And so in matrix notation, here are our y's, here's our design matrix, epsilon, but the beta vector, we're saying for beta 1 through beta k is 0. So then when you do this multiplication, this essentially goes away and we're left with a vector of 1s times beta 0. And so when we look at the hat matrix under this model, under the null hypothesis, it becomes this: 1, 1 prime, 1 inverse, 1 prime. And we call that J in our previous videos. Now, one note though, remember that let's say these were not 0, and this is the design matrix. The hat matrix would be x prime x inverse x prime, which that's transpose. But our design matrix gets rendered down to this column vector of 1s. So x is really just 1, and so that's what this represents. So in PV10 we showed that the least squares estimate for beta 0, when it's the only beta parameter in the model, is y bar, and that makes sense. If you get to pick one number that best represents the y data, seems like y bar, the mean, would be a good one. On average you're correct. Now the sum of squares regression in should be shown to this y, h minus j y. But under the null hypothesis, h is j, so this is 0. And in PV28, we were looking at the type 1 sum of squares, and we noted that the sum of squares with only beta 0 in the model is 0, and this is another justification of why it's 0. Now the global f-test tests whether sum of squares regression is 0 or significantly greater than 0, right? So if all these are 0, then sum of squares regression is 0. If at least one of them is not 0, then the sum of squares regression is greater than 0. And that's another way to think about this test. But in reality, I think about it as, are any of these predictor variables helpful or not? That's what we're testing. Now, a potential test statistic is this: the sum of squares regression divided by sigma squared. We've shown, and this is matrix notation, that it's a chi-squared with k degrees of freedom. And where does k come from? K comes from because it's the rank of this matrix, the middle matrix when it's in quadratic form. That's the rank, or the degrees of freedom. And it has a non-centrality parameter to this, but under the null, h was j, so this becomes 0. It's a central chi-squared with k degrees of freedom. But we don't know sigma squared for this to be chi-squared, so we have to estimate this. Now we can estimate it for, use an unbiased estimate, maybe the mean square residual, mean square error, that's an unbiased estimate. And then we can say, and it actually is consistent, so we can, for large n, whatever that means, we can just use this chi-squared and say it's an approximate. But we can do better. So we must estimate sigma squared with sigma squared hat. Now I say must, it's actually not must. There's probably other estimates that we can use. But when we use this unbiased estimate, it sure does make things nice. But now we have two random components in our test statistic. Now here's one more note. Under the null hypothesis, this product, and where does this come from? I minus j is here, and h minus j is in the sum of squares regression. Now under the null hypothesis, h is j, so this becomes 0. And that's going to play a part in our test statistic. So we've shown that the sum of squares regression is a chi-squared, k degrees of freedom. We've shown that this sum of squares residual is chi-squared with n minus k plus 1. So it's a chi-squared divided by its degrees of freedom, chi-squared divided by its degrees of freedom. That's an F test, with k numerator degrees of freedom and n minus k plus 1 denominator degrees of freedom. Now under the null hypothesis, the numerator and denominator are independent, right? So the random component, this is a quadratic form, and just to show the product of those matrices are 0 means they're independent. Now the chi-square or the sigma squares cancel, and we're left sum squares regression over k, which is what we have called the mean square regression. And since this goes away, sum squares residual divided by its degrees of freedom is the mean square error. And if we look at this in a ANOVA table, this is it. There's two sources of variability. So regression and residual. Some call this the error term. Those two add to the total. And then we have formulas for the sum of squares regression. We have degrees of freedom associated with these. And actually, how do you determine these? And don't tell me that it's the number of observations minus the number of beta parameters that we're estimating. And because that's a great rule of thumb. But really, it's the rank of that matrix when they're in a quadratic form. That's the degrees of freedom. Now, if you take sum of squares divided by degrees of freedom, you get the mean square. And so this is mean square regression. And then this one would be mean square residual, or it's more commonly called mean square error. And you divide those two and you get the F test statistic. Now, here's a side note. Now, the denominator and numerator are approximately 1, but under the null hypothesis. Else, the numerator is greater than 1. And let's look at that. So here, this is a chi-squared with degrees of freedom n minus k plus 1. What's the mean of a chi-square? The degrees of freedom. So on average, this is going to equal the degrees of freedom, which is 1. Same way from the numerator. Under the null hypothesis, this is a chi-squared, central chi-squared with k degrees of freedom. So on average, it's going to be k. Divided by k, it's on average 1. So 1 over 1 is 1. But when the alternative is true, then it becomes a non-central chi-squared. So the number, its expected value is bigger than its degrees of freedom. And so this numerator becomes bigger than 1. And then you divide by something that's roughly 1. And then it becomes, the whole test statistic becomes large, which then shoves it in the tail of this F distribution, which we would reject the null. Well, next videos, we're going to look at the partial F test. We're going to look at t-tests and what are called general linear hypothesis tests. That's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.